I found this recipe in a very old chemistry book, the 7th edition of Edward Turner's Elements of Chemistry, published in London in 1832 by the King's College during the early years of Queen Victoria's reign, though the recipe itself has even older origins, with its earliest iterations appearing in the writings of alchemists centuries earlier as an attempt to transmute tin into gold. To begin, we need what the book calls the peroxide of tin, our modern stannic oxide, which we're told to prepare by dissolving some tin metal into nitric acid. As the acid attacks the metal, it forms a precipitate of insoluble metastannic acid, or the hydrated oxide of tin, which gradually collects as a pile at the bottom of the flask. Simultaneously, the reaction produces highly toxic fumes of nitrogen oxides. For safety, the air issuing from the flask is passed through a series of gas washing bottles and an alkaline gas trap before being vented beneath a powerful fume extractor. Once all the tin has been converted into this white oxide, we're left with a milky slurry. It's given some time to settle before the acid is decanted off, and then the oxide is rinsed with distilled water to remove as much of the residual acid as we can. The washed powder is then dried, transferred to a tube, and bathed in the flame of a blow lamp to dehydrate it. As it roasts, it changes color, turning an orangish brown color in the heat, but a straw yellow on cooling, just as the book describes. To this yellow oxide, the book has us add an equal weight of sulfur and a half weight of ammonium chloride. Once thoroughly mixed, this powder is transferred to a flask and placed in a charcoal furnace. Immediately, the sulfur and sal ammoniac begin to sublime, clouding the glass as they condense. But as the flask gets too hot for them to remain condensed, we can begin to see the mixture again, which has taken on this vibrant orange color. Even by the first edition of his textbook, published in 1827, chemical theories were already so developed that Professor Turner could identify what elements are reacting here and in what proportion. He tells us that each atom of tin is ultimately joining to 2 of sulfur, forming a compound known then as the bisulfuret of tin, that we would now call tin disulfide, along with a gaseous byproduct of sulfurous acid, or sulfur dioxide. These fumes are again washed and ventilated. Though this sort of chemical knowledge could easily be taken for granted today, this textbook's ability to discern the elemental makeup of those atomic constellations we call molecules would have been something of a wonder in its time. After all, earlier books of chemistry, such as this one by Pierre Maquet, published only 50 years earlier, still presented the elements of nature as fire, earth, air, and water. This dramatic shift in chemical theory was a product of the chemical revolution, the culmination of the experimental efforts of generations of natural philosophers, as scientists were called back then. However, Turner's theoretical understanding of this reaction doesn't require that strange third ingredient of ammonium chloride that the recipe calls for, whose role in the reaction is never actually specified, save that on the authority of the great chemist Berzelius, the process just won't work without it. More recently, it's been suggested its role is to promote the formation of tin disulfide over the less oxidized tin monosulfide through a process that releases more toxic fumes. The presence of this sal ammoniac in Turner's recipe, despite it lacking any theoretical justification at the time, makes more sense when you recognize that it was inherited from the recipe's past, in the craft traditions surrounding alchemy that were practiced long before the chemical revolution. As the reaction proceeds, these shiny particles are tossed around inside the flask, and soon the walls of the flask are covered with lustrous flakes that look sort of metallic. Here I stopped fueling the fire. As it cools, you can see the matter in the flask has become a glittering copper-like mass. Once allowed to cool, the flask is pulled from the furnace, and the extent of the transformation becomes apparent. Though they had appeared a copper red in the heat, as they come down to room temperature, the metallic flakes become increasingly, even brilliantly, golden, telling me the reaction worked exactly as it was meant to. To get a closer look, the flask is smashed, revealing that the whole of the tin has been converted into this golden powder. This is aurum musivum, or Mosaic gold, crystalline tin disulfide, a sort of imitation gold that pops up here and there in alchemical texts throughout history. Its name, Mosaic gold, comes from the fact that artists have long used it as an alternative to gold leaf in mosaics. Its chemical formula, SNS2, makes it the tin analog of fool's gold, FeS2. This is far from the only alchemical recipe you'll find in the pages of Turner's Elements. The book is teeming with these long-standing alchemical recipes, especially those through which the chemist, just as the alchemist had before them, found their reagents in the world around them, in metals, stones, plants, and even the refuse of animals, many of which survived to Turner's time with little else changed than the common names of the substances involved. For example, this process, for extracting benzoic acid from the resin of the snowbell tree, along with the unusual apparatus here to make use of, can be found under the title Flowers of Benzoin in the Tyrosinium Chimicum of Jean Biguion, an alchemical textbook that would have been as old to Professor Turner as Turner is to us. Similarly, this description of nitric acid production can be traced to this recipe for aqua furtis in Johann Glauber's New Philosophical Furnaces, a 17th century alchemical formulary, known for its innovative use of the theory of acids and salts alchemists like Glauber had developed. Beyond these preserved recipes, the influence of alchemy can also be detected in some of the book's newer recipes, processes, and theories, the fruit of novel research in Turner's time, whose seeds were first planted by the earlier generations of alchemists and natural philosophers who came before. For example, these recipes that manipulate the distillates of wood to produce a variety of organic compounds, found in the section of the book written by none other than Baron Justus von Liebig himself, whose work is considered foundational to organic chemistry, are the descendants of earlier alchemical experiments like those performed by the alchemist philosopher Robert Boyle in categorizing the distillates of wood by their chemical activity. Chemistry first began to distinguish itself from its forebear, alchemy, in the early 1700s. However, as we see here, that separation was far from complete by Turner's time, with chemistry's deep roots in the art of transmutation it had grown out of still readily visible. How did alchemists, making use of truly ancient theories of matter, develop these recipes? And how did early chemists, working with charcoal furnaces and relatively simple glassware, come to reject those ancient ideas and gain the ability to understand these chemical transformations at the molecular level, making use of the descriptions of equipment and processes found in a number of old chemical and alchemical texts? I've done my best to reproduce the tools of a functional early modern chemistry lab, what alchemists would sometimes call a chymion. Through this series, I want to try and get an understanding of this transition from alchemy to chemistry from within. If you were an aspiring alchemist in the 1200s when you first drank the elixir of eternal youth, what would you get up to in your lab, and how would your understanding of chemistry change over the many centuries of your long life? In this series, we'll be focusing on specific texts to try and understand the theories of their authors through their own experiments. In this video, the first part of this series, I want to try and get a foothold in understanding some of the more fundamental alchemical theories by reproducing a number of experiments found in medieval books of transmutation, especially one of the most influential of the Western alchemical tradition, the Summa Perfectionis of Jabir. Then, in the next video, we'll see how these theories changed as they were applied to the preparation of medicines by reproducing recipes found in the potion-making manuals that appeared in the centuries following the Renaissance. With a solid foundation in these alchemical theories, we'll then be able to better understand the experiments and discoveries of the philosophers by fire, the iconoclastic alchemists who came to reject ancient matter theories during what historians have called the alchemical golden age of the 16th and 17th centuries. From there, we'll turn to the chemical revolution of the 18th century, and we'll see how a new invention called the pneumatic trough quite literally turned chemistry on its head, and we'll follow some of the experiments of the so-called pneumatic chemists whose work first elucidated the chemical elements as we know them today. This is the Summa Perfectionis of Jabir, a medieval alchemical textbook originally written in Latin sometime in the 13th century. This textbook would have incredible longevity, It was still considered an authority by the writing of the English edition I'll be making use of, translated by Richard Russell some 400 years later in the 17th century, and it's routinely cited in 17th century alchemical works. This longevity was in part the result of the author's strict adherence to justifying his claims experimentally, with the author consistently emphasizing the importance of both theory and practice in understanding alchemy, which is why I think it's the perfect place to start. The book claims to be the work of Jabir, the Latinized name of Jabir ibn Hayyan, a legendary alchemist from the Islamic Empire to whom centuries' worth of Arabic alchemical texts are attributed. Today, we don't actually know if Jabir ever really existed, but we do know that the vast majority of the works attributed to him were written by other alchemists of the Islamic age, writing under his name pseudepigraphically. This pseudepigraphic tradition continued as alchemy entered the Latin world, under the name Jabir. The historian William Newman, who's produced a modern critical edition of the Summa Perfectionis, identifies the authorship of the Summa, along with a handful of other works directly connected to it, with an Italian alchemist of the 13th century, the Franciscan friar Paul of Taranto. Despite the incredible volume of text that makes up the Jiberian tradition, to this day Paul's works remain some of the only Jiberian texts accessible to an English audience. The alchemy of Jabir's Summa Perfectionis revolved around understanding the alchemical processes. These are the various practical techniques alchemists would use in the lab, such as distillation or calcination. To Jabir, these processes are how we manipulate the ratios of the four classical elements of fire, earth, air, and water within substances. Because of this, these processes were both craft techniques as well as pillars of alchemical theory. Unlike today, where our elemental theory is very quantitative, relying on us measuring the specific quantity of any given element in a substance, the ancient four elements grew out of a qualitative approach to matter, where the presence of an element in a substance was believed to be indicated by the qualities that substance possessed. For example, anything that can burn must contain an element of fire within it. Because of this, elements could be described as easily with adjectives as with nouns. Rather than saying, "It contains an element of fire," Jabir would say, "It has combustibility," while anything that can melt into a fluid has aquosity and must contain an element of water. If it can evaporate, it has volatility, or contains an element of air, and if it cannot melt, it is terrestrial and must contain earth. The Summa Perfectionis presents us with an elegant symmetrical system of 8 processes for manipulating these elements. Jabir likes to describe these processes in terms of preservation and deprivation, meaning for the most part these processes are meant to alter a substance by preserving some of its elemental qualities while depriving it of the rest. For example, dissension preserves a substance's water and fire, but deprives it of its earth, while calcination deprives a substance of its water and fire, but preserves its earth. Thus, dissension and calcination are essentially a pair of opposites. Jabir's Summa Perfectionis is devoted to metallic transmutation, turning lead into gold and the like, making use of primarily mineral reagents. While today we recognize the metals as being elements in their own right, Jabir instead sees metals as compounds, or really mixtures, of two principal components he calls sulfur and mercury that are intimately combined through geological processes deep within the bowels of the earth. This mercury and sulfur theory was inherited from the alchemists of the Islamic period, grounded in older Aristotelian mineralogical theories. I don't actually have any mercury to show you, but this molten gallium looks kind of like it. Real mercury wouldn't adhere to the glass, and would instead bead up, almost like water on wax. You may know that mercury, sometimes called quicksilver, is a metal, unique for the fact that it's a liquid at room temperature, bearing both a low melting point and a low boiling point, meaning it could actually be boiled and evaporated with the furnaces of Jabir's day. Sulfur, on the other hand, is a fairly common yellow mineral, sometimes called brimstone, known for being one of the relatively few rocks that can be readily lit on fire. To Jabir, these substances we know of as mercury and sulfur are just the common forms these substances take on, and modifications of these two principles are said to exist throughout the mineral world. Rather than thinking of mercury and sulfur as these distinct substances, to understand alchemical theories, it's better to think of them as the sum of their qualities. As we go, try to keep in mind that mercury can flow like water and evaporate, meaning it's aqueous and volatile, whereas sulfur is combustible. When combined to form a metal, different ratios of these two principles were meant to produce different metallic qualities. To Jabir, to transmute a metal, all you have to do is alter the ratio of one ingredient to the other, adjusting the metallic qualities until they match what you're going for. Jabir's process of metallic transmutation typically began with the calcination of a metal. I'll start with this tin. By calcining the metal, or roasting it in the open air, Jabir believes we can separate the metal into its two principal components, which are defined by their Aristotelian qualities. The mercury principle is cold and wet. This would align it to water and mean it has aquosity, or fluidity. This is what allows the metal to melt into a molten blob. One of the reasons it's called mercury is just because the molten metal resembles the liquid metal mercury. The other principle of metals is hot and dry. This is the sulfur, which makes the metal combustible, allowing it to be burned to ash. That ash was known as the calx of the metal and was produced by calcination. As the molten metal roasts in the open air, its surface becomes covered in a dull slag. This slag is in modern terms a mixture of the metal with metal oxides formed by contact with atmospheric oxygen. However, to Jabir, it was the sign of calcination beginning, and was believed to be caused by the metal's dry sulfur principle being ejected from the tin. Because gold doesn't rust or burn to ash in a fire the way this tin does, Jabir believed gold to have relatively little sulfur in it. In his own words, Jabir says the reason calcination was invented was so that the corrupting and defiling sulfurity may be abolished by fire. To calcine this metal, I have to continuously stir the molten metal and separate off the slag as it firms, saving it in another crucible. Slowly, the bead of molten metal becomes smaller and smaller as more slag is removed. Once I've separated a good deal of slag, I throw it all back into the crucible and calcine it further. This separates the metal from the oxides it's mixed with and produces a grayer, more powdery slag. I repeat this process again and again until instead of slag we're left with just a dark gray powder mixed with beads of metal. This powder is the calx of tin. In modern terms, this black calx is tin 2 monoxide, otherwise known as stannous oxide, not to be confused with the yellow stannic oxide we made earlier. Despite all this talk of separating metals into their principles, to Jabir this calx is not the sulfur of the metal. The production of this calx is enabled by the sulfur, but it is not identified with it. Jabir treats the sulfur principle, for the most part, as being an invisible or unseen substance, what he calls an occult substance hidden within the metal that enables combustion. The word occult here literally just means unseen. From what I can tell, the only time Jabir indicates that we can actually see the sulfur principle of a metal escaping is in the calcination of copper. When burned, copper metal emits this green flame. Jabir tells us this flame is caused by the combustible sulfur fleeing the metal, and he attributes it to the greater quantity of sulfur in the high melting point metals of copper and iron. Because the calx is ash and is no longer combustible, far from being the sulfur principle, it's actually meant to be deprived of the sulfur principle. Jabir sees metals as porous bodies, with sulfur filling the pores of the base metals. As the metal is heated, the sulfur escapes, and the porous skeleton left behind collapses in on itself, resulting in a pile of ash. Because he saw the sulfur as being a corrupting impurity, Jabir believed this sulfur-deficient calx could just be melted back together to reform a metallic body, and hopefully that body would be more perfect or gold-like now that it has less sulfur corrupting it. Jabir tells us that to return the calx to its metallic state, we have to reduce it through a process called dissension. Interestingly, despite being essentially opposites, calcination and dissension are strikingly similar. The main difference is that the crucible filled with the calx is placed deep inside the furnace, and charcoal is stacked on top of it, rather than sitting on top of the coals as in the calcination. In modern terms, this allows the metal oxide to be reduced back to the metallic state by the carbon and carbon monoxide produced by the furnace, while keeping it protected from the oxygen at the surface. Crucially, despite calling the process reduction, just as we would today, Jabir does not recognize the role of the carbon, what we would call the reducing agent. To him, hiding the calx under the coals allows the calx to melt back together into a metal, while protecting it from the rising flames that would calcine it again. In this theory, a reducing agent is unnecessary. Jabir insists that when reducing tin, we urge the coals on strongly. You'll notice this produces these ethereal licking flames. This flame is actually the carbon monoxide produced by the charcoal burning in the air above it. Seeing this flame is a good sign that the interior of my furnace will be strongly reducing. After a little while, I went fishing through the embers to check on the crucible, and as I uncovered it, I was greeted by blobs of molten metal. Some of the tin I had started with had successfully returned to its original state. Jabir saw calcination and reduction as a cyclical pair, and he suggests by reiterating this process over and over again, the metal will gradually be purified of its sulfur. I added some shavings of pine rosin to act as flux, and then resumed the heating. Though I said Jabir doesn't recognize the role of reducing agents, he does recognize a utility to fluxes, which he sometimes even calls things reducing in some of his other works. I have to admit, I found it hard to pin down what exactly he thinks fluxes do, but he seems to suggest that they join with the metal's terrestrial or earthly corruption and help separate it from the metal's flowing mercury that we've been trying to purify. To Jabir, the mark of dissension succeeding is seeing the metal able to flow like water again. With the dissension complete, the tin has undergone the complete cycle once, but you'll notice it's more or less the same as how we started, no closer to gold. Some alchemists weren't deterred by this and just tried to repeat this calcination and reduction over and over. But Jabir warns us against that, and instead tries to present a theoretical explanation for why this process seems to hit a wall after a few repetitions. Jabir tells us that just as the sulfur of a metal can be burned away, the mercury principle can be driven off through evaporation. Just like mercury metal, the mercury principle can be volatile, meaning it can boil away as a vapor. And unlike the sulfur that has to be burned to escape, the mercury principle doesn't need to combust. It just evaporates off whenever the metal is heated sufficiently. This means that while calcination preferentially drives off sulfur, dissension can preferentially drive off the mercury. As we saw, Jabir thought of the calx as the metal deprived of some of its sulfur, but what happens when a metal is instead deprived of its mercury? Jabir typically used ashen sand as a flux for his calx, which he made into a paste with water and firmed into a sort of lozenge that was placed in the dispensary. Jabir tells us that one of the biggest challenges with the dissension of tin is preventing it from vitrifying, or turning into glass. By strongly heating some of the fluxed calx in the flame of the blow lamp, the calx is sintered to the ashen sand, forming a sort of glass frit. This little lump, which can no longer flow like molten metal, is meant to be the form a metal takes on when deprived of sufficient mercury to allow it to run fluid. Being that Jabir saw mercury as a perfecting principle and sulfur as a corrupting one, the net result of these two processes alone won't yield any gold. Instead, he actually says calcining and reducing tin over and over produces lead. To Jabir, alchemy perfects metals by removing superfluity and supplying deficiency, removing the bad stuff and adding in any missing good stuff. He tells us the alchemical processes we've been using are all meant to remove superfluous impurities, but that they do nothing on their own to supply the deficiencies left behind by the processed matter. Meaning, the way we've been using them so far, the alchemical processes have just been breaking things apart, making them analytic. He believes to transmute a metal into a more noble one than we started with, we also need the ability to add stuff back. Synthesis. Thus, to make gold, he believed the alchemist needed to not only separate a metal's sulfur from its mercury, but also then combine that mercury with a medicine that would supply its deficiencies, allowing it to become a more perfect metal. These medicines are his elixirs of transmutation, the most powerful of which is of course the legendary Philosopher's Stone. Jabir separates his transmutation agents into 3 orders. The Philosopher's Stone is the solar medicine of the 3rd and final order, which is meant to universally transmute any metal it's combined with into true gold. It's also, of course, the transmutation agent Jabir is the most protective of, and the processes surrounding it read more like riddles than easily replicable recipes. Luckily for us, however, he's significantly less secretive about the medicines of the lower orders. The medicines of the first order are the simplest, and are just meant to mimic the visual appearance of gold or silver, rather than actually producing those metals. The second order is supposed to approximate gold or silver, not necessarily truly produce them, but produce metals very similar to them. Unlike the Philosopher's Stone, these lower medicines are not universal, meaning you can't use them on just any base metal. They are instead tailored to transmute one or another metal in particular. Because of this, alchemists would call these lower transmutation agents particulars. To Jabir, these transmutation agents must be made out of metals themselves. He tells us the easiest metals to turn into gold are those that are already rich in mercury, being lead and especially tin, whose abundant mercury is evidenced by the fact that they can melt very easily. However, to the contrary, the best metals to make into the transmutation agents you need to alter those metals are the opposite, the highly sulfurous metals of iron and especially copper. This theory may seem weird given we've just been talking about removing sulfur. Why would we want to add any back? Interestingly, Jabir believes there's different kinds of sulfur. Though gold is said to have very little sulfur, the sulfur it does have was meant to be a rare sort of fixed sulfur. Unlike normal sulfur, this fixed sulfur does not burn, and is supposed to give gold its beautiful citrine color. He's hopeful that we might be able to find and extract some of that rare sulfur in minerals and metals that are rich in the sulfur principle more generally. This theory could easily fit in with the aurum musivum we saw at the beginning of the video, wherein the calx of tin is combined directly with crude sulfur in an attempt to produce gold. Even the ways this recipe fails still align with Jabirian theory. For example, the fact that aurum musivum isn't able to melt like true gold could easily have been attributed to the crude sulfur overcorrecting, giving the metal an abundance of dry sulfur, preventing fusion. Rather than relying on common sulfur, Jabir attempts to balance the mercurial abundance of tin with the sulfur principle taken from those metals deemed sulfurous, an idea that I can't help but think could have been used to explain the phenomenon of bronze production, wherein tin is melted together with copper to produce bronze, which bears a lower melting point than copper, but a brighter color than tin. Of course, just as with aurum musivum, this bronze is not gold, and would have failed the most basic tests, or assays as they're called, that Jabir describes for proving the identity of a metal. Instead of just melting the metals together, Jabir insists that to transmute, we have to extract the fixed sulfur of a metal through the process of dissolution, wherein the metal is dissolved with a water of acuity, what he calls his acids. In a companion text to the Summa Perfectionis entitled In Search of Perfection, he actually calls dissolved copper the water of fixed sulfur. Before we can make any of Jabir's transmutational medicines, we'll need to first get a hold of one of his waters of acuity, which Jabir believed we could separate from crude matter using some of the other alchemical processes. Two of the most important Jiberian processes are distillation and sublimation, which were both intended to separate a substance's spirit from its body. It was with these techniques that alchemists prepared their acids. Though there are many recipes for such acids in the works of Jabir, I'd like to jump forward to a later recipe that I think is of note, making use of common sulfur, or brimstone. Recipes for a powerful acid called the oil of brimstone, or the oil of sulfur, appear in a number of prominent alchemical texts from the late Renaissance, and the so-called books of secrets that were emerging at that time, such as the secrets of Isabella Corteza, or Giambattista della Porta's natural magic. However, the most detailed description I've encountered comes from Conrad Gesner's New Jewel of Health. Though the oil of brimstone is a later recipe that appeared long after Jibir's time, many alchemists identified it with the oil of vitriol, a far older acid that does appear in the books of Jibir and even those of his predecessors. I'm choosing to reproduce these recipes because, as we'll see going forward in this series, they have a particularly great historical significance, but I have to insist they're ridiculously dangerous and really shouldn't be tried at home. You'll notice molten sulfur burns with this gentle blue flame that appears only at the surface of the sulfur. Alchemists knew they could invigorate the fire with hot iron, as demonstrated here. In modern terms, just like the metal we calcined, the sulfur is being oxidized to form sulfur dioxide. Unlike with the calcination, where the metal produced an ashy calx when burnt, the burning sulfur produces no ash. Instead, the whole of the sulfur burns away into toxic fumes. The hot iron helps to evaporate the burning sulfur, producing a taller flame as the reaction takes to the air above the crucible. Jibir likes to categorize matter in terms of spirits and bodies. Bodies include the metals that burn to ash, whereas spirits include things like sulfur that vanish away entirely, needing to be condensed out of the air to be collected again. The processes to condense such spirits were called distillation if the condensate was a liquid, and sublimation if the condensate was a solid. And it's the fumes of this sulfur flame that are meant to be condensed to produce the desired oil of brimstone. Because it relies on an open flame, the oil of brimstone calls for an unusual distillation apparatus in the form of a glass bell suspended over the flaming crucible of sulfur. Immediately, some vaporized sulfur begins condensing on the inner surface of the bell. Because it's collecting as a solid, this sulfur is said to be sublimating. However, this isn't our desired product. Gesner's recipe tells us the oil of brimstone should collect alongside this sublimate as a liquid distilling out of the smoky fumes filling the bell. In modern terms, most of these fumes are sulfur dioxide, a gas at room temperature that we won't be able to condense in its pure state, but that when dissolved in water reacts to form sulfurous acid, some of which I was able to collect on a pH slip from sulfur dioxide reacting with the water the bell is cooled with. The red color indicates the presence of an acid. But if, as some claimed, this process could actually produce the infamous oil of vitriol, then the sulfurous acid isn't what we want either, and we'd need to instead make the more highly oxidized sulfuric acid. There's a couple ways this could happen, but neither of these are very likely to occur here, meaning it would take a very long time, possibly days, before we collect a meaningful quantity. It's possible an unknown impurity in Gesner's sulfur could have helped his process along, but it's also possible he was just willing to accept a horribly inefficient process. Gesner tells us 5 pounds of sulfur will produce less than an ounce of acid this way. Even if we presume his product was pure sulfuric acid, which it certainly was not, then this would still only come out to a yield in the range of a fraction of 1%. But even that could be an unrealistic expectation. A later account of the process in Johann Glauber's New Philosophical Furnaces tells us that the oil is so difficult to produce that apothecaries have just stopped selling it altogether, saying nowadays it is found almost nowhere. He suggests that some alchemists burn sulfur for weeks and only accumulate a small amount of oil, if that, meaning even Gesner's fraction of a percent yield could have been many times greater than what some poor alchemists experienced. Some alchemists found that the process could be made much more efficient by introducing water. Nicolas Lemery, in his Curse of Chemistry, tells us that some alchemists only perform the operation in wet weather, or otherwise introduce water to the bell, which all do by piping in steam from a boiling flask. This water will dissolve some of the sulfur dioxide the flame is putting out, reacting with it to form sulfurous acid in solution, which drips into the basin beneath the bell. You'll notice I've moved the reaction inside. For obvious reasons, this reaction is exceedingly dangerous in confined spaces, and I should note that I'm performing the operation directly beneath a very powerful fume extractor, while wearing a respirator rated for sulfur oxides. Introducing water this way lets us collect a greater quantity of the acid fumes produced by the flame. But even this doesn't give us the results we need. The acid we've produced here isn't sulfuric acid, but is still just the more volatile sulfurous acid, and if we try to concentrate it by boiling, it will all just evaporate away. Much like the waterless method, I never managed to get as much as a drop of oil this way. Luckily, Lemery gives us another option. This time, instead of burning the sulfur alone, it's mixed with a little bit of niter, our modern potassium nitrate, infamous since the time of Roger Bacon as the crucial ingredient that turns charcoal dust into gunpowder. Only a small amount of niter is called for, about 1/16 the quantity of sulfur. Along with this, instead of relying on moisture in the air, the earthen pan is filled with a little water for the sulfur fumes to absorb into once they've been made. Just as before, red-hot iron is dropped into the mixture, but as soon as it's lit, the cover is placed entirely over the pan, trapping the flame. Once the flame's gone out, I just let the chamber sit, allowing the water to absorb all the fumes. Looking back at the flame, you'll notice it was far more vigorous than the others we've seen, and is more orange than blue. Also, as soon as the flame ceases, the water rushes in from around the bell, while at the same time, the fire runs out of air and the crucible throws up a big cloud of unburnt sulfur powder. As the bell rests, the water level inside it continues to rise, as the gases dissolving into the water produce a vacuum of pressure. Only by the next morning had the pressure equalized enough to let water spill back out. This water is pretty acidic, but it will remain to be seen if we actually have any oil of brimstone dissolved here. Lemery tells us to filter this water, which removes any of the sublimed sulfur and leaves us with a crystal clear solution. We then have to boil this filtrate down to remove what he calls the phlegm, an alchemical term for water, especially wastewater that dilutes our desired product. Once the solution has lost most of its volume, I transferred it to a smaller boiling flask heated gently by a spirit lamp. At first, the puddle boils normally, but it wasn't too long before the boiling diminished and finally altogether ceased. Rather than steam, the puddle began to put out these white fumes. These are the telltale signs of sulfuric acid, and they mean we can remove the heat. Introducing a strip of litmus paper, you can see that not only does it turn red, but the acid promptly chars and devours the strip. This is the oil of brimstone we've been looking for, our modern sulfuric acid. Though I only managed to make a few drops, bear in mind that the flame that produced this quantity of acid burned for less than 5 seconds, rather than the days required by the earlier processes. This astronomical increase in yield is all thanks to the little bit of niter, which in modern terms is an oxidizing agent, helping to produce the more highly oxidized sulfuric acid rather than the less oxidized sulfurous acid. This niter was likely included to help the sulfur burn while enclosed, in hopes of catching more fumes. Little did the alchemists know that the nitrogen oxides produced by its decomposition can catalytically convert the sulfurous acid into sulfuric acid so long as there's oxygen present, meaning that even while the bell was at rest, it was all the while making more oil of brimstone. Much like how Jabirian alchemists thought that tin being able to be burned to ash implied the existence of a combustible substance within it, alchemists also thought this oil of brimstone was a spirit of the sulfur that was being driven out by fire. Today we know both tin and sulfur are elements, but in these alchemical theories, if a substance can be burned, then it must contain something within it that can escape, making their elemental nature effectively inconceivable. According to the historian R.J. Forbes, in his book A Short History of the Art of Distillation, it was the alchemist Andreas Libavius who first recognized this oil of brimstone as being one and the same with the far older oil of vitriol, an acid produced by distillation of the vitriolic stones. The vitriolic stones are beautiful crystals, which in modern terms are metal sulfates, such as copper sulfate, known as blue vitriol, iron sulfate, known as green vitriol, and potassium aluminum sulfate, known as white vitriol, or more commonly, alum. All three of these stones were used to produce sulfuric acid. However, alchemists also knew how to use sulfuric acid to produce these stones. Recipes for producing vitriolic stones persist in the Kitab al-Asrar of al-Razi, an alchemist who lived as long ago as the 8th century AD. and who the historian William Newman has demonstrated as being one of the major influences behind Jibir's Summa Perfectionis. For the metal, in this case I'll be using copper filings, as specified by a recipe in the Kitab al-Asrar. A small amount of the oil of vitriol is mixed with water and brought to a boil before the filings are poured in. In modern terms, the strong acid is oxidizing, or pulling electrons from the copper metal, converting it into copper ions that happily dissolve into the water. In this way, it's similar to the calcination of the tin, in that both are instances of metal oxidation. After a short while, I allowed the acid to cool, and added a little more diluted acid before resuming heating. Jabir tells us the product of a dissolution is a salt, what he classes any substance soluble in water. He also notes the similarity between salts and calxes, and in his own words, says that calcinates approach the nature of salts. It isn't long before it becomes clear the acid has taken on some color. Once I thought I'd dissolved most of the filings, I removed the flask from the furnace and allowed it to cool. Returning to it later, I found blue crystals of copper sulfate had crystallized at the bottom of the flask. Crystallization like this is what Jabir would call coagulation, the inverse of solution. I added fresh water to dissolve the crystals, which, after being given enough time to dissolve, produced a brilliant blue solution. These vitriolic stones were valued for more than just their ability to produce acid. By dipping a sheet of iron into the flask, you'll notice the metal in contact with the solution is instantly colored, and on closer inspection, you can see the surface of the iron has been converted to a shining red copper. It's not hard to understand why such phenomena would fascinate alchemists. In modern terms, this apparent transmutation is what's known as a single displacement reaction, where the iron metal is oxidized and swaps places with the copper in solution, which is in turn reduced to the metallic state and deposited on the surface of the metal. Rivers and springs flowing out of copper mines were often laden with similar compounds to this blue vitriol. It was known that iron placed in those springs would soon have their surfaces converted to copper, lending credence not only to the idea of metallic transmutation, but the idea that such transmutations occur naturally beneath the earth. That these stones could be made from acids, and that those same acids could be made from these stones, reveals a similar reversibility to the calcination and reduction we saw earlier. The symmetry in Jabir's alchemy is a product of the reversibility of his processes. Jabir, and alchemists like him, believed these processes to be natural cycles, performed all throughout nature, whose successful completion caused substances all around us to slowly change from one into the other, allowing the earth to renew itself. The very substance of the world itself was meant to be in a constant state of transmutation, like a serpent devouring its own tail, perpetually destroying itself to create itself anew. Any given thing exists somewhere between being made and unmade, the only difference being the context surrounding it. The alchemist Pseudo-Albertus Magnus, who authored the Libellus de Alchemia, describes this idea in terms of ice in cold weather melting into water in warm weather. It's not that there's anything fundamentally different about ice and water, but instead, the context surrounding them determines the form they take on. In this way, alchemists believed everything was essentially the same thing, taking on different forms in different contexts. Turning one thing into another just requires altering the context of the world around it. As Jabir says, "We alter not metals, but nature, for she by herself acts, not we." Now that we have some dissolved copper, we have one of two ingredients we need to produce one of Jabir's transmutational medicines, specifically one of the first order medicines of Venus, meaning a particular transmutation agent meant specifically to make copper appear to have been made into gold. The other ingredient we need to finish the agent is dissolved tudia. Tudia is a somewhat unique reagent among those you'll find in the works of Jabir, often taken in a crude form from a mineral known as calamine before being purified through sublimation and calcination to produce what we would now recognize as zinc oxide. For our purposes, I'll just use this pure zinc oxide. Rather than giving us everything we need in one place, Jibir likes to hide hints and crucial bits of information across multiple texts that the reader needs to piece together, a fairly common technique in alchemical writing known as dispersion. For example, in the recipe for this medicine in the Summa Perfectionis, he tells us to dissolve tadia, but he does not tell us what we should be dissolving it with. That answer is to be found in one of the companion texts to the Summa Perfectionis, the Invention of Verity, where in a section entitled Preparation of the Middle Minerals, Jibir tells us that tadia is to be dissolved with distilled vinegar. In modern terms, distilled vinegar is a pretty dilute solution of acetic acid. Because it's so dilute, I'll have to use a lot of it to dissolve this quantity of tadia. To get it to dissolve, I gently heated the mixture over a lamp. As it warms up, the zinc oxide happily reacts with the acid to form water-soluble zinc acetate, with a byproduct of water. Once the acid has been completely neutralized, having dissolved as much tadia as it could, I filtered the solution to remove the excess zinc oxide, and then boiled it down to remove the phlegm. While the solution was still hot, I transferred it to a basin to coagulate. As it's allowed to cool, the zinc acetate crystallizes out of solution. This leaves us with these nice white crystals. Once collected, I then redissolved as many of these crystals as I could in a minimum quantity of water to produce a concentrated solution. Once the water has dissolved all it will, I filtered the solution into a phial. To make our transmutation agent, Jibir just has us combine the two solutions of dissolved copper and dissolved tadia into one. So long as I've done everything right, this blue mixture is our transmutation agent, a first-order medicine of Venus. As you can imagine, after all this time, I was pretty excited to finally have my hands on a genuine Jabirian transmutation agent. So how are we supposed to use it? I'll give it a shot, but unfortunately there's some details about the procedure that I'm unsure about, so I'm not certain I'll actually be reproducing it the right way. As a medicine of Venus, it's supposed to be used on the calx of copper. The process of calcining copper is a little different than with tin. Because copper melts at a much higher temperature, instead of being melted and having its slag collected, Jibir has us just roast plates of copper and then collect the scale. Scale is just what we call the oxidation that appears on a solid metal rather than as slag on a liquid. You'll notice as the plates of copper are roasted, they turn black as oxidation builds up on their surface. This black layer is the scale we need to collect. This could be done by mechanically scraping the copper, but I much prefer the method of just quenching the hot metal in water, which causes the scale to fly off the surface of the metal in a very satisfying little poof. Doing this over and over, you can collect a lot of scale that can then be ground and placed in a fire and roasted, and then ground again and so on until eventually you'll end up with a reddish-brown pile of oxidized copper like this. This could be what Jabir means when he says the calx of copper, but it also might not be. Jabir describes the calcination of copper different ways in different parts of his texts, often making use of salts or other corrosives rubbed into the plates to help along the calcination. Depending on what process you follow and what ingredients you use, the calx could actually be a number of different copper compounds, including just being copper metal itself. In the companion text, The Search of Perfection, when Jabir describes the calcination of copper, after producing the calx, he actually tells us to clean it by grinding it with salt and vinegar until the black color of the calx has been removed. Essentially, this is removing the copper oxide and exposing the copper metal beneath, meaning his copper calx might actually just be finely divided copper metal. With all that in mind, I'll start out by making use of copper oxide as the calx of Venus. In the description of this process in the Invention of Verity, Jabir has us imbibe the medicine into the calx. The powdered oxide soaks up drops of liquid readily. To Jibir, this process of dissolving and imbibing a medicine helps it more intimately join to the metal. There's no real concept of chemical bonding in Jibir's theories. Instead, Aristotelian alchemists held to a theory of mixtion, wherein all compounds are just mixtures of their elements. While modern chemists talk about different compounds having different bond strengths, Jibir describes different substances as being more or less intimately mixed. This theory of intimate mixtion is even used to explain gold's high density. Because its elements are supposed to be combined very intimately, it's a very dense metal. Once imbibed and allowed to dry, we're left with a sort of crumbly mixture of calx and salts. Jibir then tells us to reduce this calx with things reducing, meaning a flux, though he doesn't give us a specific flux to make use of. In another section of his book, he mentions a flux for copper composed of an unspecified ratio of niter and oil of tartar, which was the basis of some fairly common fluxing compounds throughout history. For our purposes, I just added some of the imbibed calx to the crucible and topped it off with a mixture of carbon and tartar. Out of curiosity, I added a bit of bare copper wire to the crucible as well. I then placed the crucible on live coals in a large furnace, which is then filled with more charcoal and covered. I urged the fire on strongly for some time, trying to get the crucible to a glowing heat. The copper wire acted a bit like a thermometer, showing me both by the color it glowed and the fact that it wasn't a puddle that the furnace wasn't yet reaching sufficient temperatures to melt copper. Though already by this point the furnace is hot enough to produce zinc fumes, and as such it requires both the respirator and fume extractor to be done safely. On uncovering the furnace to refuel it, I found the crucible had become covered in a yellowish powder, and that the mixture had decreased in volume substantially. I added the rest of the imbibed calx with more flux and put the cover back on. Urging the coals on as much as I could, I brought the furnace up to as high a temperature as my little hand bellows could manage. This reduction step is crucial to Jibir's process of transmutation, and is when the medicine and metal are meant to unite. You may remember, when reducing the calx of tin, the process of reduction was said to break stuff apart, separating the metal's earthly corruption from its fluid mercury. But here, the same process is being used to bring stuff together. Jibir's processes are neither inherently synthetic nor analytic. Instead, they're said to bring together things of a like nature, and separate things of contrary natures. The metal's watery mercury is separated from its contrary earthliness, but is joined to the agreeable medicine, whereas that cast-out earthliness is joined to the flux, which to Jibir is almost always some substance considered to be earthly. After a short while, I uncovered the furnace again and pulled out the copper wire to see if any changes had taken place. On cleaning off the surface a bit, I could make out an encouraging streak of golden metal, though interestingly, the yellow color only appeared in the upper middle of the copper wire, where it had been exposed to the material I added halfway through, while the crucible was already hot. Unfortunately, I was completely unsuccessful at getting the calx to reduce, much less fuse together into a unified body. I decided to try the process again, but this time I preheated the crucible to a red heat before adding the mixture, and made use of copper filings rather than copper oxide. This was certainly a much more exciting way to do it, as the crucible threw up loads of these colored flames. You can see the green flames of copper and even some blue of zinc, but also orange flames, as the tartaric acid from the flux and acetate ions from the medicine are decomposed, throwing up organic decomposition products that combust in the air. I imagine this sort of thing would have seemed like a good sign to Jibir. As we saw earlier, he would have held these flames to be the metal's combustible sulfur escaping, leaving us with, hopefully, only the unburning fixed sulfur. Once everything had cooled, I cast out the contents of the crucible. Again, I failed to melt the metal into a single body, but I was genuinely surprised to actually see some glimmering golden metal among the crucible's contents. It evidently hasn't all been made into gold. There's a lot of copper reds and oranges mixed in there, but interspersed through them are these brilliant little nuggets of imitation gold. This is orichalcum, what we know of as brass, or an alloy of copper and zinc. Well, today brass can be made by melting together zinc and copper due to its high reactivity and low boiling point, making it very difficult to isolate. In Jibir's time, the European world still lacked knowledge of zinc metal itself. Meaning, unlike the bronze we saw earlier that was known to be an alloy of two metals, to the medieval world, brass appeared to just be copper modified, or as Jibir would say, cleansed by Tudia. Orichalcum was actually used as proof of the possibility of transmutation in other alchemical texts, as seen here in the Libellus de Alchemia. They didn't think it was gold, but more so on the way to gold. It wouldn't have passed any of the trials of the time, and as such is the product of the lesser first-order transmutation. That Tudia, or refined calamine, had this ability to modify copper was no secret. Nor was this process invented by alchemists. It dates back to the ancient world, and you can find similar medieval recipes for orichalcum, or calamine brass, in earlier craft manuals like On Diverse Arts by Theophilus, wherein we're told to mix calcined calamine with charcoal and roast it with copper metal. Theophilus even tells us to preheat our crucible to a red heat before casting in the mixture. Jabir references this established practice of orichalcum production in his Book of Furnaces, and elsewhere seems to expect some of his readership to already be experienced in working with Tudia. However, I don't think Jabir thought of this medicine as just making the usual orichalcum. Rather, Jabir appears to have been applying his alchemical theories to the phenomenon of orichalcum production in hopes of improving the product. And he insists that the recipe can be taken further still. In contrast to Jibir's medicine, the recipe for orichalcum in the earlier work of Theophilus makes no attempt to sublimate the calamine into Tudia, or to dissolve that Tudia. To Jabir, these extra steps would serve to purify the ingredients and unite the medicine more intimately with the metal being treated. One reason I like this recipe is just how clearly it shows Jabir actively applying his theories to the world around him. It is, after all, those attempts to use these theories predictively and test them practically that would allow them to develop and separate science from speculation. In the next part of this series, we'll see how these medieval theories fared when applied to the organic substances made use of in the potion-making practices of 16th and 17th century alchemical medicine. And this time I don't mean transmutational medicines for making base metals into gold, but human medicines meant to treat symptoms of illness, cure disease, and also maybe give you eternal youth. Thanks for watching. As always, if you have any questions, comments, or corrections, please feel free to comment below. Any corrections will be added to the pinned comment once I've verified them. If you'd like to dive deeper into the topics I mentioned in this video, look to the sources in the video description, where I'll include both the resources I used for this video, as well as links to a number of lectures from those same historians that you might enjoy. The best book you can pick up if you want to learn more about the history of alchemy is Professor Lawerence Principe's Secrets of Alchemy. To my longtime viewers, I'm sorry for dropping off the map for a bit there. Originally, I had intended this video to be about Lavoisier's Elements of Chemistry, but I kept wanting to add this or that and ended up with this series instead. I'm not great at getting these videos out when I intend to, but I'm confident there will be many more videos coming in much less time than it took to get this one up. I greatly appreciate your continued support. Thanks again, and happy transmuting.